Hello there. I am here with 3 examples about rational roots theorem, which can be super tedious, but I also want to make sure that I'm able to give you guys some shortcuts. But I've got 3 problems, and this first one that we're going to do is we're going to just focus on the rational roots. The second problem will focus on the all of the roots, including complex and multiple roots. And in the third problem, I'm going to start with the roots and have you go to a function, and one of those roots is complex. So here we are, starting with this very first problem. I'm going to solve for all rational roots using the rational roots theorem. Remember that you have Desmos, though. Desmos is a really huge tool. So the rational roots theorem itself is we're going to start with P, which is all of the factors of our constant, both positive and negative. So I can multiply 1 and 6, can make 6. Other factors would be 2 and 3, and all of those are plus and minus. I'm going to move on to Q, which is all of the factors of the A coefficient, which again are also plus and minus, and in this case I've got 2 and 1. Then for the actual rational roots theorem, for all of the rational roots, they are the combinations of P over Q. So again, we've got plus or minus for everything, and I'm going to go through them, and I'm systematically going to put each of these over 2. So I'm going to go 1 over 2, 6 over 2, 2 over 2, and 3 over 2. Then I'm going to go back and I'm going to put again 1, 6, 2, and 3 over the other possible Q factor. So I'm going to get this list of 8. So 1, 1, 1, 1. As we go ahead and reduce these, we'll see that some of these are repeating numbers. So let's go through and do that. So we get 1/2, 3, that's a 1. 3/2 is unique, but then that's just another 1, so I don't have to worry about that. The next value is a 6, a 2, and then 3 again. So at least I've knocked it down to 6 possibilities. However, unfortunately, it's really possibly 12 because it's plus or minus each of them. The next step is a particularly tedious part, which would be to actually go in and to plug in each of these. F of 1/2, F of negative 1/2, F of 3, F of negative 3. Find out what all of these are, and so on and so forth, right? We're not going to sit here and do that. That's crazy. But what we want to do is we want to identify when we get out a 0, because remember, there's such a huge connection between roots and zeros. The zeros that we have, we can also use Desmos to help us identify those. So let me pop in a little Desmos window here. I'm going to put a little browser in here. I'm going to shrink it up. So I know that it's going to be really tiny for you here, so I apologize. Actually, let me make it big. Sorry. And then we'll shrink it up at the end. So I am going to go to Desmos, and I'm going to type in my function as it's written. So 2x cubed, oops, got to get that exponent up there. 2x cubed minus 9x squared. It's really hard to type on this second window. For some reason, it doesn't like it. Plus 7x plus 6. So here we can see, okay, I've got a root definitely of negative 1/2, 2, and 3. So I'm going to go ahead and I'm going to kind of write those down off to the side. Negative 1/2, 2, and 3. That is confirmed by looking at, let me shrink this up. Oh, it doesn't want to shrink up. Hey. It won't let me shrink it up now. Okay, I'm just going to go ahead and delete this because now that you've seen it, we don't need it any further. And so I'm going to go ahead and delete that element. Okay, so we have these here. We do see those in our list, the negative version of that and the positive version of this one and this one. And those are where I would get a 0, and at f of 2, I would also get a 0. So this is where my zeros are. All of these other ones are going to be some number, and I don't care what that number is. It means that it's not ending on the graph at a 0. It's not a root. But if I know that my root is negative 1/2, I now know that I can factor this, and I actually can factor f of x if I needed to. I can factor this to x plus 1/2. Remember, there's always some a value in there. X minus 3 and x minus 2. Oops, I forgot my x. The question is, I don't really know what the a value is. I can go back here and I say, oh, I know that the a value is actually 2. And what happens when I plug that in, this is not a necessary part of the problem. I just want you guys to see the connection. When I distribute that 2, I can get rid of this fraction and I get this nice factor. And then it looks kind of like factored nicely, right? Anyway, that's all there. Once you've done these and connected it to the rational roots theorem, you're good to go, because all it's asked for is solve for the roots, and here's the roots. This is my answer, and we're done. I just wanted you to see the connection to the function. No problem. Now we're going to solve for all roots. Now this is a little bit trickier. Also notice that it's a quartic. It's a 4th degree polynomial, so we're going to have 4 roots here. We could go through the whole rational roots theorem, but you can also, again, use Desmos to help you. So I'm going to pop the window in here so that you guys can see it. Browser, graphing calculator, I'm going to punch in the function as it stands, which I do have written down here so I can cheat a little bit, even though you guys can't see it, which is x to the 4th plus, what is it, plus 2x cubed plus 5x squared plus 8x plus 4. Okay, so we're seeing this kind of crazy graph right here. If I squish it up, you can see that it kind of has that parabola shape to it, but it's a little flattened out in the middle. And I can see right there that it's just touching that x-axis and bouncing away at -1, which is telling me that -1 is a multiple root. So I know that this is going to happen multiple times. So let's see, I'm going to delete this piece and go back into the group. So I know that I'm going to have factors of x minus, not minus 1, plus 1, and another factor of x plus 1, because I know that there's a multiple root. And then the question is, what's here? What's left? And what are the roots of that piece? Because I only saw this 0 in the graph. But remember that the fundamental theorem of algebra tells us that there must be 4 roots. Because I can see here that there's a 4th degree polynomial, I need to have 4 roots. I know that -1 is happening 2 times, but what in the world are the other ones? There were no other intercepts, which is telling me that these must be complex. And complex roots always happen in conjugate pairs. So this makes sense. At this point, what we're going to have to do is some long division or some synthetic division in order to help us figure out what in the world is left here. So let's step aside and do that for a second. So I'm going to start with some synthetic division. It's much faster. I'm going to go ahead and start with all of my coefficients of the original function. First coefficient is 1, 2, 5, 8, and 4. I don't have to worry about any placeholders. My divisor in this case is the actual root. The factor is plus 1. I'm going to divide by x plus 1. My factor, or my root, is -1. Drop down that 1, multiply, add, multiply, add, multiply, add, multiply, add. I got to a 0. That's confirming that -1 is indeed a root. But also it's now letting me know what is a little bit of that piece that's left there. So what this translates to, remember we started with 4th degree. We've divided away a single linear function or factor. So we're dropping 1 degree down to x cubed. 1x cubed plus 1x squared plus 4x plus 4. So far I have factored this into x plus 1 times x cubed plus x squared plus 4x plus 4. But again, I know that there is a double root here, so I can divide again. So I'm going to go ahead and divide again. I need to kind of be consistent with colors here. It's getting a little tricky, but so I'm going to go ahead and divide again. This time again with the coefficients, I've got a 1 there, a 1 there, a 4 and a 4, again with a -1. Drop down the initial, multiply, add, multiply, add, multiply, and good. I do get to a remainder of 0. What does this translate to? This translates into, again, we were at a cubed. This was 1x cubed, so we're dropping down to 1x squared plus 0x plus 4, and we're done. So this is x squared plus 4. What I have now factored to is x plus 1 x plus 1, x squared plus 4. So here's my one root of negative 1. Here's my other root of negative 1. And we are left with what roots come from this. Your best bet here is to go ahead and rely on the quadratic formula. So we're going to rely on the quadratic formula. We have x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You guys have learned this before, and it is back. It's an important one. Negative b. Well, this is x squared plus 0x plus 4, so b is 0. So there's nothing there. So it's 0 plus or minus the square root of 0 squared minus 4 times 1 times 4. I'm going to extend that so it's clear. All over 2 times my a of 1. I feel like I'm going to write out of space and need to squish this a little bit more, but now I've got plus or minus, let's see, 0 squared, negative 4 times 4 gets me a negative 16 all over 2. 16 is a perfect square. I'm still left with the plus, oops, I don't know why I did the equal sign twice. I'm still left with a plus or minus. 16 has a perfect square of 4, or a perfect square root of 4, and the square root of the negative 1 factor inside of there leaves me with an I, and then I have a 2. That simplifies a little bit further into plus or minus 2i. I'm going to have to squish one more time. Oh gosh, it didn't squish all together. That's very interesting when it does that. Okay, so I've got to squish a little bit more. This is a long problem. I actually know what all of my roots are now. I have negative 1 twice, plus 2i, and minus 2i. These are my roots, and this is the answer to this question. Next problem. Give a function with a complex root of 2 plus 3i. It's always x minus a root times x minus another root times x minus another root, dot, 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 all times, so, well, it can't be another a out there, but some other a coefficient. In this case, I'm given 2 of the roots. I don't need to worry about any other possibilities. I'm just going to focus on these 2. But there's not 2. It's only giving me 1. Remember, complex roots always happen in pairs. There must be the conjugate 2 minus 3i. So one of my factors is going to be x minus 2 plus 3i. And the other factor is going to be x minus 2 minus 3i. I draw these far apart because then there's these big parentheses. It's very messy very quickly. X minus this number, x minus this number. But now I can do a little bit of algebra to multiply these out. The first thing that I'm actually going to do is I want to get rid of that interior parentheses by distributing the negative. Notice it turns into plus 3i. And then I need to actually multiply them out. This is my function. This is actually f of x at this state, but it's not simplified because we're never going to have an I in our final function. So how to multiply this out? There's a trick to this. If we actually apply this grouping right here, I hope that you guys can see that we actually have a difference of squares because I have the same term here, the same term here. One of them is minus and one of them is plus. So with the difference of squares, it makes it so much easier to multiply out. I get the first term squared minus the second term squared. Much easier now. Multiplying this term out, I get x squared minus 4x plus 4. Multiplying this one out, I get minus 3 squared is 9, and I squared. Remember from your previous lesson, I squared means it's a negative 1. So this becomes a plus 9. And on my last step of simplifying, and boom, there we go. If I were to go back into the quadratic formula now, the result of the quadratic formula for this equation would be right there. And that is the function for which my complex roots, one of my complex roots is 2 plus 3i. All right.